So today, Vahan's going to be presenting, and it's a really interesting paper about sampling directed acyclic graphs, which are specifically used a lot in causal modeling, which is when you try to come up with a model which describes the actual relationships which determine how things play out in the real world. Like the really simple causal models that we hear about are in medicine, where you're trying to figure out like how a medicine affects a patient who has a disease. And those DAGs are actually usually like two variables, which is like, or three, which is like patient, medicine, outcome, and the patient and the medicine point to the outcome. So anyway, I'm going to pass it over to Vahan now.
Thanks, Peter. Thanks for the introduction. I'll quickly also rename myself. I don't know how to do it. Anyway, my name in Zoom is Entran, but my name is Vahan. If you don't know me, and welcome to the paper club. So today, as Peter said, we are going to talk about an interesting paper that we found from ICLR this year. This was actually in posters. A lot of it's actually quite interesting paper. If you look at every little detail, every detail they used, they are not actually novel, but the way the paper is constructed, the way they solve a very important problem, and there is novel, and the results are actually very encouraging. So let's go into the details. So I highlighted important parts everywhere in the paper, so I'll try as a reminder to talk about those. So the main idea here is that we want to learn on dots, directed acyclic graphs, in a differentiable fashion. Differentiable matters because, as we will see, if you don't relax the problem to make it differentiable, it's well, first NP hard. But even if you make other assumptions and simplifications, it's actually computationally very expensive to learn. And then we will also do some more experiments using to learn on the graph with the variation and inference, and then we'll compare it with a few other methods, state-of-the-art methods. Okay. Well, DAGs are actually very common, used everywhere. Specifically, the idea is that you want to model causal relationships. So these appear in many applications, like causal discovery in biology, economics, or planning. Again, you model an event in your graph, and then the next event that's a causal that has a causal relationships with the previous one, you model with a directed edge. And it's acyclic because, well, in many cases it doesn't make sense to have cycles, and we will have to reinforce this acyclic behavior in our models. Cool. So generally speaking, here if you look at Formula 1, we have observed data, which is the X matrix. G is the graph. So we want to maximize some score over the data and the graph. So the score depends on the applications, on the specific application. And with a constraint that G is sampled from all possible tags. Obviously, this problem is super exponential. I think it's even worse than exponential. It's NP hard, and there are a few citations showing that. But basically, a common trick is to relax this discrete constraint into a smooth continuous constraint. So H is a smooth function, and it can often be G is the weighted graph, and the important thing is that H is 0 when graph is actually DAG, right? So it kind of creates smooth, continuous relationship between the discrete points in the space, if you think about it, so that we can actually do gradient descent. Then the score functions can be cross entropy or mean squared errors. You will actually use both later on for experiments, depending on the problem you are trying to solve. Okay. Then what else can we say about the problem setting? Right. So one common way to solve this constraint problem is by doing Lagrange relaxations, which basically means to enforce this constraint, you actually do sequential projections, and each projection is an optimization problem, which makes the problem computationally expensive. So for each, instead of solving one optimization problem, you end up solving a sequence of optimization problems, which makes the training process exponentially computationally very expensive.
I think, sorry, I think practically actually it's the calculation of H that tends to be fairly expensive. I think the dual optimization by itself is not that massive, because it's in principle just numbers. You increase the number of steps, maybe you do by 2, but it's calculating H is because H has to have knowledge of the whole graph, right? That can be quite expensive.
Yes, and the expensive in terms of number of nodes in the graph. Yes, but the problem is we have to compute H many times, right? We don't do it only once, but because of the nature of this Lagrange optimization methods, we need to do it many times, which makes the computation very expensive. Right? Is it right, Arvid?
Absolutely, yes.
Cool. We'll come back to this plot here when we study the details of the algorithm, or actually should we do this now? Let's look at the figure 1 right now, because that represents the main idea, which is basically if you have a DAG, which it means we also have an order, a topological order. I think in the paper they never say topological order, because you can have, in generally speaking, it's an order in the graph, which means you can go over the nodes in the graph in an ordered fashion, and it's possible because there are no cycles, right? You would never come back to the previous nodes. But the cool thing about that is you can create that by creating a permutation on the adjacency matrix. So if you have the permutation matrix, which defines that order, then you have the edge matrix, which is the U here. You can actually, which is a upper diagonal matrix, okay? Because it's a directed graph. You can apply the permutation on the edge matrix to construct a new adjacency matrix, which is an adjacency matrix of the graph, but it creates a new ordered matrix, right? This is a way to decompose our adjacency matrix into upper diagonal version, which will define the topological order. This is a trick we use for sampling later on. Okay, and this is actually also differentiable. This makes the problem differentiable. Cool. I think that's what we talk here. And the two.
Obvious that it's differentiable at this point.
Sorry.
Is it obvious that it's differentiable at this point? It's.
Well, we will have to do a few more tricks there, right?
Yeah.
We will have to replace argmax with the softmax and a few other tricks, but this is part of it. There are a few other steps we have to do actually.
Yeah, because typically when you sample, right, you sort of draw a random number? Why would drawing a random number be something that is differentiable, right?
Right, so we have to replace Bernoulli with a differentiable distribution, and then we will have to replace also argmax with a softmax, and basically we use this Gumbel distribution several times.
Yeah,
to achieve that.
Also something that the forwards and backwards propagation are slightly different, right? So they're not.
Yeah, that's actually the fun part, right? We'll go into this later on, but that's actually interesting because on the forward pass they leave the non-differentiable bits, but on the backward pass, because they need a gradient, they replace it with the non-differentiable bits with the continuous differentiable relaxations, which is kind of clever, right?
Very much so.
And actually, there was one thing I wanted to discuss, but we'll go to it later when we look at the details. But yeah, that's making the problem differentiable is one of the main contributions here, and as a result, we end up with a DAG sampling algorithm that performs almost consistently better than state of the art. There are a few exceptions, but it's a magnitude times faster to train, which is a huge deal. Instead of training your model for 12 hours, you do it for 2 minutes, I think. That's an incredible improvement.
One question I had was, do you assume that you always have the same variables that you have to construct the DAG for?
What do you mean same variables?
So like this method, does it only work when all of your DAGs have the same number of nodes and each node is a specific variable that you already know?
What do you mean you already know?
So like all the DAGs are 3 nodes and the nodes are like patient, treatment, outcome. You know, so
yes,
like,
we assume that all nodes have been observed.
All nodes are, but are they the same? Like, say you sample 2 different DAGs from this method. Does each DAG have the same number of nodes? And are all the nodes the same variables between them? So there's like, you can find a variable in one graph and in one DAG and then point it directly to it in the other.
I don't know actually, because usually I thought they sample only one DAG, right?
Yeah, but the number of nodes is not constant during the sampling, right? So between one run the next,
well, when they sample the U matrix, do they give like the size of the matrix as an input, or is it a fixed size?
I want to say they give the size of the matrix, right? So what is your observable? You observe D nodes, and each node has, I think, a single number as observable, right? So that's the problem setup. And you can in principle treat it as a very, very large matrix, n samples by D observations, right? And then try to find which one of these are related by putting in the adjacency matrix.
Yeah,
and
actually,
I think
you're right, because the U matrix is actually just, it's not a matrix. It's you feed in 2 nodes and then it gives whether they're connected or not.
Exactly. So you give exactly the matrix is a number of nodes in this permuted space, right? So you rotate the space to be purely upper diagonal, but then the number of valid connections is actually what is being trained, right? That is and I think we're going to talk about this later. There is going to be some sort of prior on U that forces it to be low sparse, exactly.
So we use prior as a sparse regularization, which is also pretty interesting because it seems like a thing borrowed from classical signal processing.
Yeah,
but we'll go to that also. Yeah.
I don't understand why you need to enforce sparsity, like if there's sparsity in the data set.
I think we can discuss this maybe also when I present the paper, because it's actually, there's a whole lot of funkiness going on there. There's first of all, the problem is that this problem is not invertible, right? So from the causal structure, from the data, you can't typically infer the causal structure, and so you would have degeneracy of solutions, which is broken by sparsity. By sparsity, you take two valid solutions and make one better than the other.
Okay. Should we go slowly, because I feel like we are jumping forward.
Sorry.
And we are discussing things that should come later, and if it makes things a bit more convoluted. But on that note, I remember now that it's important to mention that the order that we defined, the topological order, is not unique. Okay, there can be many valid topological orders, which will also become important, as Arvid said now, when we have to enforce sparsity, because there are many topological orders that can be defined on the same DAG. Okay, so they define a quick overview of related work here. So they define 3 areas of related work. One is solving this as a discrete optimization problem. Kind of mentioned this, but to make this problem tractable, we have to add assumptions. Things like the tree width of the DAG, number of parents for each node. So we have to constrain the space to make the problem tractable as a discrete optimization problem. The other approach is continuous optimization. So this is basically taking the discrete version and then creating continuous relaxations from it. So this is that's similar to what we do here, except these continuous relaxations do not guarantee that during the training, at all times, the generated graph is actually a DAG, because the constraint becomes a soft constraint, right? So it can be violated. There is a penalty, but it can be violated. However, in this paper, we build a method that enforces the DAG constraint during the optimization by adding projections. We'll see later how it's done. And the other area is sampling-based methods. So when we define the continuous versions, we can also formulate the problem as an MCMC, except that we know that that's also so we do the partial order computations, the topological order computations using MCMC sampling, but that's actually computationally very expensive. They give one example here that one of the recent methods using MCMC sampling requires suggests 12 hours of sampling time from the posterior distribution on a DAG with only 100 nodes. 100 is tiny, right? However, in this paper, we managed to solve the problem by much faster, it's like 3 minutes, by formulating it as a variational inference problem. Okay, and we do the sampling more efficiently, but we'll go to it later. Okay, so these are the 3 related areas, work areas. Cool. Any comments here? Okay. So first here we define what is a DAG. We have a graph, vertices, edges, ordered. So edges are ordered pairs of nodes because it's directed. There are no cycles, which means we can define a linear or partial order. We spoke about this earlier. And then there is this theorem, which actually formalizes what we spoke about before about this figure here, that we can represent the just symmetrics as in terms of a permutation matrix and an upper diagonal matrix. Okay. So basically, this upper diagonal matrix serves as a adjusted matrix. Okay, we will use this for sampling data. Cool. Now we have to create a few relaxations, right? So first, how do we make the edge sampling differentiable? Well, we replace the Bernoulli distribution for edges, because edges either exist or not exist, right? It's a 0, 1. Naturally can be given by Bernoulli distribution, but instead we replace it with a Gumbel softmax distribution. So I wrote down the Gumbel distribution here. Basically, it looks like this. There is a spike at the mean. So if you have two parameters, the mu here, which defines this peak here, and beta defines the shape, right? So if you do mu 0, beta 1, is you would have something like this, top being at 1. Okay. And the softmax here is to replace the argmax, because when we sample from a distribution, like which node do we take, right? So if you take the argmax, that makes the problem non-differentiable. So instead, we use this softmax form. There is also a parameter theta, which controls, which is an interpolation between a one code encoded distribution, categorical distribution. So if you allow controlling how discrete you want your distribution to be, okay, between one hot encoded and continuous distribution. So the theta can be used to control that. And here the main complexity is to create the upper diagonal U matrix, which has the quadratic complexity in the number of nodes. Okay, they have all the details in the appendix as well, actually. No questions? Okay. The other non-differentiable part that we have to make differentiable is the permutation sampling. So the permutations are discrete because which permutation do you take, right? That's a discrete problem, but again, we replace it with another version of the Gumbel distribution. I actually don't know the details of Gumbel Sinkhorn, but it's a similar trick, right? You replace sampling from permutation with the Gumbel distribution. So instead of 0 1s, which define that permutation, you make the distribution smoother. But if anyone has more experience with these distributions, please pitch in. Okay, I guess it's fine. And this is actually interesting. I didn't actually quite understand how exactly they do it, because they say we use the Hungarian algorithm to use this to compute discrete permutations in forward pass. Now, Hungarian algorithm isn't resource allocation algorithm. I'm not entirely sure how it translates into this DAG here, but does anyone have more experience with graph algorithms?
We did another paper where they mentioned it and I was presenting and I read up on it, but I really don't remember. So I could try to do I'll look it up really quick.
That's fine.
What's interesting is, I think here it says it's also n to the third, which I think, if I remember correctly, was also the same complexity as the smooth method.
Oh no, but they discuss two smooth methods. One is cube, the other is quadratic. Right? There is another version when they manage to find the quadratic complexity.
Very good. The other thing, which is actually quite interesting, but if you think about it, what does it mean that we sample permutations and the upper triangular matrix separately? Right. So imagine our U is a very stable distribution, very precise. Then essentially we say, yes, we know there are 2 or 3 nodes that are strongly coupled with strength X.
Mhm.
But the permutation might be much looser defined and could be saying, okay, it could be these two nodes that are actually related, or these two nodes which are related, which is interesting from a bias perspective, right? What kind of assumption it makes about the problem.
But if you sample separately, how do you guarantee that the multiplication remains the DAG?
Say it again.
So if you sample from the permutation matrix
Mhm.
and the upper diagonal U matrix independently, how do you know that the multiplication still represents the DAG? Or does it not matter?
That's the theorem, right? The theorem says that any permutation matrix times any upper triangular matrix gives you a DAG, right? That's how I read that. But,
oh, yeah, that's true. Yeah,
but of course, in
yeah.
reality, I might be misunderstanding that might still be completely different graphs, right?
Yeah, of course, because any permutation will keep the same graph. You change the order, the linear order, but you still keep the same DAG.
Yeah, but the permutation could, in principle, also be among different nodes, right?
Among different nodes.
So there are certain permutations that are equivalent, but they could also be if you keep u constant, right? So the permutations tell you then essentially which nodes actually are connected in via the u adjacency, and so I would think just by sampling from that, when you get different different graphs, like different nodes being considered causal or not. I'm not quite sure about that, to be honest.
Yeah, it could be, because at some point they also talk about projecting onto valid DAGs.
Yeah. So any of these samples should be a valid DAG, but they might still cover a large variety of different nodes that be connected by this.
Yeah, I think so.
Can I add something to this here?
Of course.
Yes. So I had a quick look on this paper, so I didn't get all of the bits correct, but at first instance, your theorem 1 can in a sense confirm that after permutation you would get a DAG, but it doesn't confirm that there'll be a causal relationship among the nodes. That would come as hence after you've optimized your problem, and slowly you start building causal relationship among the nodes. That's how I imagined it.
So if you create a different graph, you are changing the causal relationships.
Yeah.
But as you train the model, that improves.
You pick the ones that are more sensible.
Yeah, I think the p distribution on the permutations should essentially find one class of permutations that are equivalent to each other, right?
I suppose they could with further experimentation improve their sampling as well, so that not more how would you say, so some DAGs would not make sense in terms of causal relationship, but some DAGs would, so they can with experimentation improve it. But the main idea that I got was from that initially this was done using a Bernoulli distribution, and for there was one we just mentioned earlier about Gumbel's sinkhorn that was also used for approximation. Essentially, the convex relaxation have been used in the past, but in other problems like GANs. But here, as Vahan pointed out, that it significantly improved result in terms of speed. So that was the first part of the paper explaining. I think if we go further, maybe they'll explore how they made sure that more causally, I don't know the word for it, I'm going to say more causal DAGs along with the optimization problem.
So I think the improvement in training time is not so much because of convex relaxation, but because of the changing the algorithm from from Lagrangian projections to doing gradient descent. Because I think the other relaxation is also convex. Right?
The relaxation is not convex. There are multitudes of solutions. I think the speed update here might actually be more between this and the MCMC, because the MCMC was particularly slow. When I tried these other methods in practice on reasonably small graphs, like maybe 20 by 20, it was quite fast. I think I don't know whether it speeds it up by that much.
Yeah, the improvement. So they did experiments on 100 size and 400, I think. The difference gets much bigger when you get to 400. Actually, if you want to look at the performance, there is this nice graph, which is actually the quadratic complexity. This is actually between their own two methods. But if you look here, it's like on the 200, the improvement is already actually pretty big, but it gets, no, this is not time. Time is here. This training time here. So the bigger graphs have much bigger improvement in time, right?
Yeah.
Well,
I don't know which methods these are actually, whether which ones were the smooth ones and which ones not. But yeah, it looks much faster, definitely.
So these are all smooth. So
okay,
the non-smooth ones they put in the appendix. Because there's also another detail we should look at, because it's also a bit suspicious. But anyway, back to sampling. We're looking at the results at the end, yeah?
Sure.
Right. So the other part is doing the sampling in a differentiable way. Again, we do similar trick. Oh wait, I didn't mention here. So for the permutation sampling, the Hungarian algorithm-based method, which is actually a really old one, has QB complexity. But then they also propose a different relaxation, which achieves squared complexity. So this one we will also see in experiments. This relaxation is actually much better, but it also allows differentiable sampling. The idea here is that you sort the permutations, but they use a soft sort, which is because sort is also not differentiable. So there is a differentiable version called soft sort, and this and they replace the another argmax with a softmax. But maybe we should go into too many details. The idea is that we find the differentiable permutation for sampling. Okay, and none of this is novel, right? So they are all taken from other papers. All these ingredients. And if we put all this together, there is this. This is basically the algorithm, right? They say it's just a few lines of code, but actually they are calling a few functions here, which I suppose need to be implemented. So sample permutations. This is from the Gumbel synctern, or actually the Top K. Gumbel Tom K is another more efficient version. So we sample a pi, and then we inverse the pi by taking the transpose, right? And then, yeah.
Yeah, I think because it's actually not pi transpose, it's p transpose. It's a different thing altogether.
Oh, so this p. Wait, what is this p? I thought it's the.
Probably just a typo.
Yeah, I thought it's the pi. But yeah, I think it's just a typo. So there is no p. Is there a p? I think it's just a typo, right?
Probably. But do you know what the arguments for the transpose are? The 0, 1?
No, that's why I put a question mark.
Okay.
They made the code public. Maybe we can check the code, but I didn't check the code, obviously. And then we sample edges according to the differentiable sampling we discussed before. We make the triangular mask and then do the multiplication, right? Inverse times masks times pi, which is the decomposition we did, multiplied by the Johnson matrix. Okay. This is the differentiable DAG sampling algorithm. Next, we discuss how we can do variational inference with the same principles. Basically, we have a parent X observed, a bit of noise between the parent and the child, and then we want to learn a function that can predict, give a distribution for the xi for the child, and we are learning both the true parent and the true causal mechanism, right? Both of these we aim to learn, and then we write this as an optimization problem again by maximizing the expected score over all DAG subject to the prior distribution, the probability distribution over all DAGs. So this P is the distribution over all DAGs, which we can, well, first two steps, two things happen between 4 and 5. First, the constraint becomes a regularization term with a lambda here, and we replace this distribution with a KL divergence, right, between the distribution and the prior, and we use this regularization term to enforce sparsity on the generated graph.
Is it really forcing sparsity, or is it because the prior itself is a sparse distribution?
Because the prior is a sparse distribution.
Okay.
Because we minimize the distance from a prior distribution.
Yeah, but,
right?
but in principle, the prior wouldn't have to be sparse.
No, but no, we just choose it to be sparse.
Yeah.
Yeah. Good point. Right. So there's the probabilistic learning. There's the loss function, and we maximize over the parameters theta, phi, and psi, if I say the names correctly. These are the parameters. Yeah. And the variational inference part is where, well, this is where we replace the KL divergence with the sparsity enforced prior. I'm just thinking we should leave a bit of time to look at the results.
Yeah, I'm just thinking, what was the score actually? Where did the score come in? Because that is actually where it gets quite interesting. Why? Yeah, so typically they force some kind of score, which is probably the likelihood, but the likelihood is
yes, it's the log likelihood. I'm trying to find it.
Yeah.
So these are about the training time, consists of 3 steps. Differentiable sample. So these are the same steps, right?
Yeah, it's I think in step 2, right? It applies n transformations, f theta, blah blah blah. It's this xi estimate equals the functional form of ai dot x. I think that is ultimately this thing that all of these methods try to learn or train, which is problematic actually if you think about it, because on the right hand side, you only apply x actually once, right? Say
what do you mean you apply x only once?
Well, causality imagine you have a deeper graph. Let's assume f is a linear function, right? Which could be just some kind of identity or a matrix that rotates it a little bit. In that case, the idea is that you can have causal relationships that is A causes B causes C, right? If you do, however, such an application on the right hand side, you only apply X and this A essentially masks X once. You sort of deliberately lose any deeper causal relationships if there are any, because a source essentially never sees anything that is removed further than one step, I think. And that is, and I think that the way out of this is to say that the graphs are sparse, so sparse that they actually never have any causal, quote unquote, causal relationship that is deeper than by one step. And I think because I don't know whether they refer to mathematical papers in here, but I think that was always the kind of sneaky assumption that yes, we show causality if causality is defined to be one step deep and looks very much like a correlation. And
you mean we are defining a Markov model?
Yes, so yeah, pretty much that. I think that is we were saying that xi relates to xj via more or less a linear sort of thing. And yeah.
Well, if there is a dependency, if there is a causality, but if there is a ABC, there is a causality from A to C, there should be a link from A to C as well, which still remains a DAG.
Yes, but of course that would not necessarily be the causal structure you're interested in, right? And that is actually also where this gets really funny when you look at how the data is generated, because they actually generate data, I think, using such a data generation process that deliberately cuts out any further interaction terms, which is,
well, it's in the assumptions, right? In the assumption here, that's the assumption, right?
Yes, but is exactly. But if you think about it, can you evaluate such an assumption in a single step? And no, you can't, because, or generally no, you can't, because a similar equation also is of course true for the parents, right? So if how do you evaluate such a structure model, right? You evaluate the root. From the root, you calculate the first set of parents, the first set of parents, next set of parents, and so on. This needs at least as many number of steps as there are parent rows or like the depth of your graph. And I think when you go back to this, but the thing you optimize is you only optimize the very first step. And then of course in the synthetic data, I don't know whether they do the deliberate, probably not, create data where this parent, like double parent correlation is not there, because they generate the data from this single step approach.
Can I add something to this, Avi?
Yeah, please.
So I have a bit of knowledge on KLD-based regularization, and if first to get started on the right corner, is it the fact that the solution is sparse? There will be too many graphs that will point to the same thing. Is that the problem that you're asking?
It's more like say you have a DAG that has A causes B causes C. Because if you're really strict about sparsity, such DAGs are very, very, very unlikely, right? Because they have essentially are squared in the order of connections.
So then, can you end up with a weighted graph then, with weights indicating the strength of the relationship?
Yes, and this depends on the regularization, actually, because again, here there's no way you can actually find causal direction. I think they mentioned even in the paper that they say And because of the sparsity, because you enforce, I think, sparsity also on U, small weights are preferred, which means that a direction xi to xj or xj to xi, which are mathematically equivalent, except that the weight would be one over the other. So suddenly it sort of breaks the symmetry and actually chooses the one that is smaller. So
yeah, they mentioned in the experiments because they observed that sometimes the algorithm performs worse on undirected version of the same graph because the relationship can be either way.
yeah, and I think the insight here is more to say it's forget about causality. It's there is you don't learn causality, but you find relationships is probably a better phrasing of the whole problem.
Yeah, and as well, I know that the regularization that I wanted to talk about has a mixture of the fact that there's Bayesian model averaging as well as there's an intrinsic Occam's razor, which if I understand correctly, Occam's razor favors those graphs that will be simple as opposed to complexly related. So that's a major thing about KL divergence based regularization. It has an intrinsic Occam razor component that helps you pick your solutions, your models, your graphs, whatever that is.
Yeah, I mean that is what the sparsity assumption is, right? So that is nature always sparse in this sort of sense? I don't know. Probably.
So at least in signal processing, there are theorems proving that sparsity holds, and it makes you actually find the right solutions. In compressive sensing, it's like quite old theory, but there is theory behind that. Here, I think it's just assumptions. Maybe it's too soon to build theory on that.
Yeah, it's I think more a tool to remove noise from signal, and with the assumption that any true signal can handle sparsity, whereas noise can't.
Okay, let's quickly look at the results. But before that, I actually encourage everyone to go to the open review page and read the reviewer comments here. There is a lot of interesting discussion happening there, which I had a quick look, and there is a lot to think about this work. If you're interested, the open review puts all the reviewer comments out there publicly. Well, you don't know who wrote the reviews, but you can see their reviewer comments and the editor's reasoning for decision, okay? Because the paper actually wasn't just accepted, but it was accepted also for a poster session. But the discussion, I think, was very interesting there. Cool. Quick experiments, well, hypertuned parameters and everything. One interesting I thought I had was normally this lambda regularization argument, at least in linear, no, well, not linear, but in classic compressive sensing, wouldn't be fixed. So you would start from a higher value and then you would decrease it. Here they find the fixed lambda, which is fine. They do grid search for hyperparameter optimizations. They compare against a few algorithms. Let's look at the table here. So the first three are synthetic data sets with increasing number of nodes. So this ER and SF are synthetic, so 200 nodes, 400, 200 nodes. On all of those, our method performs so much better. So those are the various ROG measures. So directed, undirected, and then the AUC ROG, and the PR is the precision recall ROG, actually. And the higher means better. Our algorithm is so much better, but as Arvid says, this synthetic data has been generated in a way that our assumptions hold. in more realistic data, which is actually really hard to find. Then they mentioned this in the introduction, that a lot of times it's hard to find realistic data with ground truth because you can't because of biological ethical constraints. There is one pseudo-real data set where our algorithm is either best or second best on all metrics. This other one is I think maybe the only human protein interaction data set where again we are either best or second best, so comparable results, right? But the main selling point for this algorithm is the training time, which is magnitudes faster, and also for inference time, again about 10 times faster for inference time. This is mostly, they explain here, this is mostly because instead of doing 10 successive optimizations, they do just one. With this successive optimization is a problem with the Lagrange optimization algorithms, because they do successive projections, each of which is an optimization problem with quadratic or cubic complexity. Okay. Another interesting thing. So here they also compare the two methods they use for sampling. In theory, the top one should be cubic, the bottom one quadratic, but actually they look like more like linear and cubic. But that's fine, right? Those are worst case complexities. So in practice, but the relationship still holds. So they actually use the top K, Gumbel top K sampling. That the top one is the Hungarian method-based one. Okay, let's scroll down. One last interesting bit here, which I found cool, is that they have an ethics statement that says always question our algorithm. And also it says that because it's so much faster, it's good for the environment. And they made everything, all the data and code available publicly, which is also great. Cool. Last few minutes of comments.
That was actually something I thought was really interesting about the paper and good, was how much of an emphasis they put on like reproducibility. They have this ethical statement, and despite the fact that they have so many baselines, I think they did a very comprehensive comparison in terms of like hyperparameter tuning the baselines and everything. It probably took a lot of work just to do that, like maybe 2 or 3 weeks just to do the experiments the way they wanted, maybe even longer. And it would cost money because of the compute.
Yeah, that's actually great. They have more experiments in the appendix, because all these methods here, these are the continuous relaxation based methods. The discrete ones, which require pre-processing, post-processing, are in the appendix. They are computationally more expensive, but performance-wise are very similar. Actually, performance-wise they are not worse. So but they put them in the appendix because here we focus on differentiable methods. Cool. Any more comments? Okay, so I guess we can end recording here.